This is Nandika, and this is my lab report for Lab 4. So, as for the introduction, the purpose of this lab was examining the motion of a spring mass system, where the mass swings in an arc while oscillating on a spring, and then we were able to compare this to the predicted and observed motion of mass. And we did this through GlowScript and Tracker, and then we were given footage of the experiment, so then we put that into both of these softwares to be able to use Python to then make our predictions and then be able to benchmark those against what actually happened. So as for the preview of the main result, we modeled position versus time graphs, and they were similar to the predictive graphs, and they both oscillated, forming a sinusoidal graph. As for the key concepts, we have the energy principle, which is the change in energy of a system and equals the work done on the object and its surroundings. We also had Newton's second law, where we computed the updated positions and velocity of mass as it oscillated. So here we can see energy principle, which involves the equation for kinetic energy, which is 1/2 mv squared, the equations for gravitational potential energy, which is mgh, and then the gravitational spring potential energy, which is mgh, and then the potential spring energy, which is 1/2 ks squared, and then the total energy, which is the sum of all these kinds of energies. F net here was the force of gravity plus the force of spring. F gravity equals mg, force spring equals negative ksl. The momentum principle was V final equals V initial plus F net over n times delta t. V final equals V initial plus V final times delta t. The system here was the earth, the spring, and the mass. The surroundings were the gravity and the spring. So as for the actual experiment, here we have the initial conditions. The ball mass was 0.42. Position was as we were given in the experiment, and the gravity is 9.8. The gravitational potential energy and gravitational spring energy and the kinetic energy were all inputted according to the equations that we explained previously. And then we have a picture from the actual experiment where we are using Tracker to be able to track the position at different time intervals. The prediction model with the calculations can be found here. So we calculated the net force, then we applied the momentum principle, and then we calculated the energy principle. So here we can see delta K, gravitational potential energy, the change in gravitational potential energy, spring potential energy, the change in spring potential energy, and the kinetic energy. We were then able to get the computational model results from GlowScript. So here we can see that the green line is the change in the spring potential energy, delta K is the blue line here, and then the red line is the change in gravitational potential energy, and the green line is the change in spring potential energy. Then we also have another graph here. It's the x position versus time. The red line is the experiment, the blue line is the model, as we can see here, and we can see the sinusoidal graph, and that the experiment has a little bit of noise, and is not as perfect of a sinusoidal graph as our model was. And then we have y position versus time. So here we have the model, which is the blue line, and then the experiment, which is the red line. And once again, the experiment is not as perfect of a model is not as perfect of a sinusoidal graph as our model is. So here we have the computational model results continued. So the blue dot is what our model is like in theory predicting, and then the red dot represents what actually happened, and as we can see, they don't always match up, and then there is some discrepancy, which is to be expected because conditions in the real world are affected by other factors. This is the final trajectory. So as for interpreting the computational model results and the sources of error, so using a greater delta t led to a smaller observed accuracy in the model. Predictive modeling assumes no external forces on the spring when air resistance is in fact acting on the observed model. So continue. Is the energy principle satisfied? Yes. There are no external sources acting on the predictive model, so the change in energy must be 0. This can be seen in the change in energy versus time graph by the orange line being 0. So as for comparing oscillation periods in x and y directions, x versus time was 1.69 seconds plus 1.68 seconds, total, and then plus 1.72 seconds over 3, leading to 1.696 seconds. Y versus time was 1.51 seconds plus 1.56 seconds plus 1.49 seconds over 3, which equals 1.53 seconds. Subtracting these gives us a difference of 0.166 seconds. Since the difference is negligible, the spring potential energy is quite accurate, and the difference can be accounted for in extra forces and surroundings and in the observed model. That's all I have. Thank you. Have a great day.